Okay, hi. We are still working sort of on the same section of this learning target that we've been working on this week. And I realize that this has kind of been a little bit tedious and it will get better, I promise. We're still working on evaluating and simplifying radical expressions. We have basically, after today, we'll basically be done with all of the things you need to know there. Um, and then next week, we'll start talking about what rational exponents are and how they work. Okay, so let's just do one practice problem from like what we did last lesson, because I want to just make sure that you're on the right track with it, and also it's kind of hard. So let's do it. Let's look at what's on the bottom of the fraction here. I want to see what is it that I need to make perfect cubes with the number, with the x's, with the y's, and with the z's. Okay, so let's start with the numbers. 9 is 3 squared. So we're almost there. Ooh, that's a horrible color. So hold on, let me just make that a little darker. Okay, so let's do it like this. 3 squared. Okay, so what are we missing to make a perfect cube? We need another 3. So we have to multiply by the cube root of some stuff. And so I don't know what it is yet. I'm not all the way there yet, but I do know one part. I do need a cube root of a 3, because now these two, this and this, will give me a perfect cube. Okay, so I need a 3. I got to put that on the top also, so let's just remind myself of that. So whatever I put on the bottom, I have to put on the top. Okay, I have two x's, so I have x squared, so I need another x. I need 2 more y's, and then I need a z squared also. All together now, when I look at these two radicals combined, those two are gonna multiply to give me a perfect cube in every part. And so that's good, because that's what I'm looking for now. On the bottom, that didn't stay blue, that's too bad. Okay, on the bottom, I end up with the cube root of, well, 3 cubed, x cubed, y cubed, and z cubed. All of those things have exponents that are 3 now. Okay, what do I get on the top? So now I have the cube root of, all right, well, I have 3 squared, I have x squared, I have y cubed, and just 2 z's, so z squared, like that. Okay, on the bottom then, I can rewrite this as, well, 3xyz on the bottom. On the top, only the things that have exponents that are 3's can come out of the radical. So I just have a y on the top, on the outside of the radical. And then on the inside of the radical, I just have to copy out whatever else I have down. So I'm going to rewrite 3 squared as 9, x squared, z squared. Okay, now there's one more thing we can do to simplify. This y and this y divide to 1. And so what do we end up with? We have, well, cube root of 9x squared z squared over 3xz. And this is my final answer. And it's kind of weird that the y's disappear. The y's kind of drop out of the problem. But it also makes sense because of all of the things that I've done. So far, all I did was I multiplied by something that was equivalent to 1. That's this thing. That's the critical step there. Choose something that's equal to, like the top and the bottom are the same, that will get rid of the radical in the bottom. So that's why this is the rationalized version. That was super exciting. Okay, so today we're working on adding and subtracting radical expressions. And so there are 2 things that you really need to check before you can actually add 2 pieces together. The first thing you need to check is the index of the radical the same? And that means, is this number right here the same? And for those 2, it is, because they're square roots. These 2 are also like radicals because they have the same index. They're both index 3, so they're cube roots. These are also index 2, so they're square roots. Yeah, okay. Well, here's the thing. Oh, the other thing you need to check for is the radicand. The radicand is the stuff inside the radical. Is that the same? Otherwise, it's not like you're combining terms that aren't like terms. So that's the issue there. So here's what I see on this one. I have 1 square root of 2 here, and I have 3 square roots of 2 here. Well, altogether, I have 4 square roots of 2. So my answer is 4 square roots of 2. This is not too bad. Really, this is the same idea as writing x plus 3x. Well, that's 4x. That's really the same idea as 4 square roots of 2. The like term, the variable, or the thing that it has to be like, is just the radical now. Okay, so let's take a look at this one. Immediately, you should be like, oh man, the indices are the same, but the radical is not. So let's do a little simplifying here, but then I think we're going to find that we're not going to be able to simplify this. So 25 is 5 squared. So I can rewrite this as 5 squared xy. Okay, so that's all fine. This side, there's not really anything I can do here, so I'm just going to rewrite it, 5xy. Okay, so then what happens now? So now I just have 5xy over here, square root of 5xy. But now I can pull out this 5, and I can say, well, the square root of 5 squared is 5. So now I get 3 times 5 square roots of xy. And now we get, okay, square root of 5, square root of 5xy plus 15 square root of xy. Well, now we really can see that the two the things in the radicand they're not the same. So this is as far as we can go with this problem. There's no more simplifying we can do because I can't pull anything out of this radical to make it so that they're like terms. Okay, this one. I have 1 cube root of 7 minus 5 cube roots of 7. How many do I have? Well, I have -4 cube roots of 7. Again, this is the same idea as if I had x minus 5x. Well, this would be -4x because they're common terms. This whole part is like what we have for our x's. Not that part, just this part. Okay, a lot of circling going on, I realize, sorry. All right, there it is. So today is about adding and subtracting. These are the two things that you need to check before you can add the two radicals together. So can you have the same index? Yes, you need that. And you need the stuff inside the radical to be the same. So the radicand has to be the same too. Okay, couple of cautions to caution you about. So here's the deal. You have to make sure the radicals have the same index. I might try to trick you and I might give you one that looks like it's sure going to be able to be combined, at least today. We'll get some tools for it next week. But I might be trying to be a little tricky here, but these cannot be combined right now because they are not like radicals. Okay. Another thing that you can do, and you can just check what happens when you put this in your calculator and this in your calculator. That's not a true statement. So let's just go ahead and write a rule here. If you have the square root of a plus the square root of b, this is not necessarily the square root of a plus b, okay? So this is not a conclusion you can create. So just draw a big old red box through it. This is not a thing. Yeah, they're not like radicands, and so you can't combine them. Okay, the third caution that I have for you is sort of a pro tip. Sometimes you might get something that looks like this, where it really looks like there's nothing that's like in here, but you might end up with something once you start doing a little simplifying. So let's take an example of that. Okay, so let's just look at the square root of 28. Square root of 28 is, well, 4 times 7. Okay. And I noticed that 4 is 2 squared, so I could write it, this is the square root of 2 squared times 7, and then this would give me the square root 2 square roots of 7. Okay, so this is just this part right here. What about this part right here? Let's just deal with the 175, square root of 175. Well, 175 is 25 times 7. And so I could rewrite that as 5 squared times 7, which would be 5 square roots of 7. Okay, let's keep going. 63 is, well, it is 9 times 7. And 9 times 7 is the same as 3 squared times 7. And so we end up with 3 square roots of 7 here. And now these three can be combined. I can write 2 root 7 minus 5 root 7 plus 3 root 7. And what do we get here? Well, this is interesting. 2 square roots of 7 plus 3 square roots of 7 is 5. And then minus 5. Our answer here is 0. This seems really surprising because these numbers don't look like they're related at all. But they are. So that's kind of just a caution for you, and a little tip is to start looking at how can you split up each radical from the very beginning so that you can come up with like terms halfway through the problem. Alrighty. So now let's talk about a couple more things that we can do here. We've seen some adding some radicals, and now let's talk about we've seen something like this. This almost looks like factored form of a quadratic, or it looks almost like complex number multiplication. So two things that we kind of have some instinct about. So let's take our 4 plus 2 root 2 and our 5 plus 4 root 2. And we're going to use box method multiplication on this. Seem like a trend? Okay, so 4 times 5 is 20. 2 root 2 times 5 is 10 square roots of 2. 4 times 4 square roots of 2 is 16 square roots of 2. 2 square roots of 2 times 4 square roots of 2 is 8 times square root of 2 times the square root of 2. Okay, so let's do a little combining the like terms and simplifying some things down. This is, let's just look at this part first. So square root of 2 times square root of 2 is square root of 2 squared, which is 2. So now we have 8 times 2 in this box. So this box is actually 16. Okay, so now what are the like terms with 16? Well, it's just this one. So we have 20 plus 16. So we have 36. And then let's look at these two. So these two are like terms also. So you have 10 square roots of 2 plus 16 square roots of 2. So we have 26 square roots of 2. I can't combine these because they're not like terms. This one has a radical in it and this one does not. Also, square root of 2 is as simple as I can make it. So this is my final answer right here. Okay, so you can use box method multiplication just like we have done a lot of times this year to do this type of multiplication. Here's one for you to do by yourself. I will go through it after you try. Okay, here goes. 3 minus root 7, 5 plus root 7, box method. Okay, 15, negative 5 roots of 7, 3 roots of 7, and then, negative 7 square root of 7 times square root of 7. Okay, so what do we get here? Well, this is negative 7 because the square root of 7 times the square root of 7 is the same as the square root of 49, negative square root of 49, and the square root of 49 is 7, so we get negative 7. That's how I got that. Okay, let's see, like terms with that. So I have negative 7 and 15. That gives me 8. And then these two add together, and they give me -2 square roots of 7. The square root of 7 is not a rational number. It doesn't give me a nice answer, and so I can leave it like this. Let's have you try this one also. This one is a little bit interesting. Okay, same method and everything. But this one does come up. Who wrote all these square roots of 7? This one does come up with a little bit of an interesting answer, so that's why I'm going through this. So I get 25 here. I get, just like we got on the last one, it would be -7 here. Here we get -5 square roots of 7, and here we get 5 square roots of 7. Okay, so check this out. What do we get? Well, we get these two together, and that gives me 18. And then these two add to 0. And so my answer here is 18. And this seems like a surprising result because we started with radicals and we ended up with something that is not a radical, but they're equal. The reason for this is that was a conjugate pair. Conjugate pairs look like A plus B and A minus B. The A and the B, it doesn't matter what they are, they're the same thing. But when you multiply them, you get a kind of an interesting thing here. And so I'm going to do this example as just through the formula, but I'm not going to expect you to just use the formula. You're certainly welcome to use the box method anytime you want to. If you dig this, then that's awesome. That's great. Just go with it. If you're like, this doesn't make any sense, that's okay. Just use the box method. Okay, so let's start by identifying what is A. A is 6 because it's written first. It's right here and here. So it matches this spot and this spot. B is square root of 12. And I know that it's B because even though it's written in opposite order, remember that it doesn't matter what order you write multiplication in. So you can write this as A, whoa, that's an X, A minus B times A plus B. So either way, these are the same. So it doesn't matter which one is which. So B is square root of 12. So my formula says my answer is going to be 6 squared, minus square root of 12 squared. Well, the square root of 12 squared is 12. So I get 36 minus 12, which is 24. If you think back a little bit to last class, we talked about rationalizing the denominator. That's what we did at the very beginning of this video too. And we said we don't like it when there's a radical in the denominator of the fraction. And the way to get rid of this when you have a binomial or a thing that has a plus in it, or a minus, is you multiply by the reciprocal, or sorry, not the reciprocal, the conjugate of that thing in the bottom. So the conjugate of 1 plus square root of 3 is 1 minus square root of 3, because we know when we take the conjugate, we get a whole number. But here's the thing, if you multiply the denominator by that, you just change the value. So you have to multiply the numerator by it also. I suppose I should write the whole thing in the right order. There we go. And then you're going to get something that's equal to what you started with. Here's the thing, the reason for that is all of this is really just worth 1 because it's the same thing divided by the same thing. So you're not changing the value of this expression at all. It's just that you have a clever form of 1 that allows you to simplify the denominator and make this denominator a rational number, a nice number. Okay, so let's multiply out the numerator. We can just distribute. So we get 12 root 12 minus root 12 times root 3. We'll deal with that in a second. I don't want to simplify that yet. Let's use the box method to simplify the numerator, or sorry, the denominator. 1 plus root 3, 1 minus root 3. Okay. I get 1 root 3, negative root 3, and then negative 3. Okay, so these two add to 0, so I don't need to deal with those, but these two add to -2. So we get -2 over here. Now let's do a little simplifying with the numerator because I think there's some stuff we can do there. So, square root of 12 is square root of 4 times 3. 4 is 2 squared, so we can rewrite this as square root of 2 squared times 3. 2 squared times 3 is, well, okay, so then we can take this 2 and rewrite it as 2 square roots of 3. Okay, so this gives us, we know that this is 2 square roots of 3 minus 2 square roots of 3 times root 3. Well, this right here is root 3 times root 3, which is just 3. I suppose I should keep the denominator there. Okay, so this gives me 2 square roots of 3 minus 2 times 3. Okay, all divided by -2. I notice that I have a 2 in every piece here, and so we can rewrite it as, we can do the divisions, and we can say, okay, well, this would just give me 2 square roots of 3 divided by -2 is negative square root of 3, and then -2 times 3 divided by -2 would give me 3. So we can rewrite our answer, and typically we write our answer as whole number first, 3, and then radical minus root 3. So there's our answer right there. A whole lot of working to get there, but you can rationalize a denominator that has a binomial in the bottom of it, meaning there's a plus, by multiplying by the conjugate over the conjugate of the denominator. I think it would be good if you tried one example. So here's one for you to try rationalizing and then simplifying. Go. Here it is. So let's multiply by the conjugate of the denominator over the conjugate of the denominator. So we're going to have 3 plus 2 root 5. 3 plus 2 root 5. Okay, so top we can just distribute. So we can write 7 plus 14 root 5. Bottom, we got to do box method. So, and maybe you're noticing a little pattern here, but it's going to be 9 minus 40. I think, let's just check our work. So 3 minus 2 root 5, 3 plus 2 root 5. Really, all I need to do is, well, I know that this box and this box is going to add to 0 because of the pattern that I've been seeing. So I can rewrite this as 9, and then this is going to be, okay, -4 times 5. Whoops, that was my mistake. So it's not 20, it's 40. It's not 40, it's 20. So this is minus 20. Okay, so the bottom of the fraction is now -11. And there's really nothing else we can do here because that's it. They're all, like 7 and 11 are both prime, so there's nothing simple that I can do there to simplify there. 5 is already prime, so there's also nothing that I can take the square root of there, so that's not going to work. So that's that. This is my final answer.